Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the concept illustration problems on buoyancy, as well as we will discuss the mindset and the approach which we need to follow while attempting these questions. So first of all, you can see that this is a container in which there is a liquid of density D. It is filled over another liquid of density 2D. And on the interface of both liquids, a solid is floating whose length 3L by 4 is in the upper liquid and whose length L by 4 is in the lower liquid. So we can say that 3V by 4 volume of this solid is in upper liquid and V by 4 volume of this solid is in lower liquid. So we have to, this solid is also in equilibrium, and we have to find out the density of this solid. So what we'll do, we'll say that the buoyancy acting on the solid due to the first liquid as well as the buoyancy acting on the solid due to the second liquid will be balancing out mg, and this is due to the fact if you are thinking that why the liquid 1 is applying a uplifting force on this solid as its base is in the lower liquid. So this is a genuine question. I'll repeat the question again, that most of the students say that the base of this solid is in the lower liquid. So why you are adding the buoyancy of the upper liquid on this solid? So this is a genuine question, and let us discuss this question in two ways. So first of all, we say that when a solid is being immersed in some liquid, then it displaces the liquid, and in order to restore the liquid at its original position, the liquid tends to throw out the solid out of the liquid, and in that tendency it applies a buoyancy force on the solid. So while discussing that the buoyancy will act or not, we should always focus on finding out that whether this solid has displaced some volume of that liquid or not. So you will see that this solid has displaced some volume of the liquid 1, and hence we will definitely say that the liquid 1 will apply some buoyancy on the solid in the upward direction. The same is the case with the lower one, as some volume of the solid is in the lower liquid, and hence we can say that the lower liquid will be applying some buoyancy force on the solid in the upward direction. So this is a clear-cut scenario. Now by the second method, we can also say that if this liquid is filled above this liquid, so the pressure at this point, the point which is at the bottom, so pressure at this point, let's suppose it is P, so this pressure will be due to this liquid also. So due to this liquid also, the pressure at this point has increased, and hence while writing the force in the upward direction, we are indirectly adding the force applied by this liquid also. So that force will be exactly equal to the buoyancy. Okay, so difference of the net force applied by this liquid is exactly the buoyancy. So we can directly add up the buoyancy and we can calculate the total force acting in the upward direction. So we can say that buoyancy 1 plus buoyancy 2 is balancing out mg, and buoyancy 1 will be the volume of solid in the upper liquid. So if V is the total volume of the solid, then we can say that 3V by 4 volume of the solid is in the upper liquid. So it would be 3V by 4 into density of the upper liquid is D and into G, plus the volume of the solid in the lower liquid is V by 4. So it would be V by 4 into 2D into G, and that is equal to mg. So cancelling this G with G, so it is 3VD by 4 plus VD by 2, and that is mg, and m will be equal to sigma into V, where V is the total volume of the solid. So cancelling V with V, this will be equal to 5D by 4, and this will be equal to the sigma. So the value of sigma will be 5D by 4. So now let's move on the next question. In this question, you can see that there is a wooden plank of length 1 meter, and the area of cross section of the plank is constant, uniform, and this plank is hinged at the bottom corner of this vessel, and this vessel is filled with the liquid till height 0.5. The specific gravity of the plank is 0.5, which means the relative density of the plank with respect to water is 0.5, and we have to find out the angle theta made by this plank with this container wall. So let us see this question. Let us assume that this plank is dipped in the water by a distance of x. So obviously we know that mg will be acting at the center of mass, and this would be mg, and center of buoyancy will be this point, which is at a distance of x by 2, and this is hinge. So we have to balance the torque of buoyancy and mg about hinge. So torque of mg is equal to torque of buoyancy, and torque of mg will be mg into this distance. So the total length of the rod is 1 meter, so this half length is 1 by 2, and this will be 1 by 2 sine theta, 1 by 2 sine theta, and it would be equal to buoyancy into this distance, this one, and this will be x by 2 sine theta. Okay, so it would be buoyancy into x by 2 sine theta. So cancelling sine theta by 2, sine theta by 2, mg will be equal to buoyancy into x, and mg will be area of rod, cross section area into length is 1 and density is 1 by 2, and this is g, and buoyancy will be immersed volume will be x into a, density of water is 1 g, and this is x. So you can see that the value of x square is equal to 1 by 2, and x will be equal to 1 by root 2. This is the value of x. So if we now say that the component of x in vertical direction is x cos theta, so x cos theta is this one. So x cos theta is 1 by 2, and x is 1 by root 2, cos theta is 1 by 2. So cos theta will be 1 by root 2, and theta will be equal to 45 degree. So the correct answer of this question is 45 degree. Now let us move on the next question. Now in this question you can see that there is a solid hemisphere which is just pressed inside this liquid in such a way such that the free surface of the liquid is just coinciding with the top point of the hemisphere, and the force applied by the liquid on the curved surface in y direction is F1, and the force applied by the liquid on the bottom of the hemisphere is F2. So we have to find out the F1 and F2 ratio, and we have to neglect the atmosphere. Now in this question what it is trying to teach you is the fact that how to calculate this F1. Now by default you would be thinking of integration, because at all these curved surface points the force of liquid would be radial and the pressure is variable as we are going into the depth. So we have to integrate the y component to find out the net force acting on the curved surface in the y direction. But obviously this should not be the approach to follow in the exam, because integration takes lots of time. So what we'll do, we'll calculate F1 by some different method. We know that F2 minus F1 is equal to buoyancy, and hence F1 will be equal to F2 minus buoyancy. So by this way we will be calculating the value of F1, and F1 upon F2 will be equal to F2 minus buoyancy upon F2, and it would be 1 minus buoyancy upon F2. Now the value of buoyancy will be volume of solid immersed, which is the 2 by 3 pi r cube into density of liquid into G, and the value of F2 will be the pressure at this point. So pressure at these points will be R rho G and multiply by the area of the base, which is pi r square. So the value of F1 upon F2 will be equal to 1 minus buoyancy. Now buoyancy upon F2 is 2 by 3. So it would be 1 by 3. So the correct answer will be C. Now we move on the next question. In this question, you can see that there is a cubical block of side A by A by A, and there is a coin of mass m which is kept over this cubical block, and this system is floating in a liquid of density rho. Now when this coin is placed over the block, then the height or the length of the cubical block immersed in the liquid is x1, and when this coin is removed, then the height of the block immersed in the liquid is x2. So we have to find out x1 minus x2. Now obviously we can see that initially the buoyancy B1 was balancing m plus mg, and when the coin is dropped into the liquid, then buoyancy B2 is balancing only mg of the block. So the difference of buoyancy delta B will be mg only, and this difference of buoyancy will be equal to difference of volume of solid immersed. So if let's suppose initially the length of the block inside the liquid was x1 and finally it is x2, then the change in the volume of solid immersed will be x1 minus x2, which is delta x into A. A is the area of the base. Now area of the base will be A square because base is square, and into rho into G. So cancelling G with G, so we can say that delta x will be equal to m upon A square into rho. So the correct answer will be option A. Now we move on the next question. In this question, you can see that initially this mass m was hanging with this spring being in air, and the reading of spring balance A was 2 kg. So which means clearly that this mass is 2 kg. And separately, when this container filled with liquid is kept on this pan, then pan was reading 5 kg. Okay, so now what we have done, we have kept this container on the pan or weighing machine, and we have dipped this block along with the spring in the liquid. So we have to find out the new readings. So obviously we know that initially this is mg and this is kx initially, but when it is immersed into the liquid, then the buoyancy will be acting in the upward direction and mg will be acting in the downward direction. Net force in the downward direction will be equal to mg minus buoyancy, and this force, which is some reduced force, is stretching this spring, and therefore the reading of spring balance will be Ra will be less than 2 kg obviously. Okay, and we know that this buoyancy is applied by the liquid on the block, and hence we know that buoyancy follows the action reaction law. So this block will also apply this reaction of buoyancy, which is equal to the buoyancy obviously, and the initial weight of the liquid plus container was 5 kg. So the reading of pan weighing machine will be obviously greater than 5 kg. So we can say that A option is incorrect and B option is correct, C option is incorrect, and D option is incorrect. So the only correct option is option B. Now let's move on the next question. In this question, you can see that there is an ice cube which is floating on the interface of oil and water. Partially it is in the oil and partially it is in the water. Now this ice cube gets melted completely, and we have to find out that whether the interface will go up, will go down, or will remain at the same level, and the level of topmost level of oil will go up, will go down, or will remain at the same level. So let us compare this scenario with the case in which if the ice was alone floating in this water. This is water. So the buoyancy will be balancing mg of ice, and buoyancy will be Vd1, which is volume of water displaced in first case when the ice was floating alone, Vd1 into rho of water into g, and that is equal to mg. So we know that Vd1 is equal to m by rho w, and this is the exact amount of volume displaced, which is equal to the volume of water formed due to melting. This we have already discussed previously. But now when this ice is actually floating in the interface, then the buoyancy of oil plus buoyancy of water will be balancing the mg, and therefore buoyancy of water will be, this new buoyancy of water will be less than the old buoyancy of water, which means that the volume of liquid displaced now 2 will be less than the volume of liquid displaced initially, but volume of liquid formed is same, therefore volume of liquid displaced now is less than volume of water formed by melting of ice. So if more amount of water is formed by melting, then we can say that this interface will go up, and obviously we know that there is some amount of air which is trapped inside this ice. So when that air will escape from the system, then the complete overall volume of the system will decrease. Hence we can say that the top surface of the oil will go down. So the interface and the uppermost surface of the oil will rise, interface will rise, and the uppermost surface will fall. So the correct answer will be A. Now we move on the next question. In this question, you can see that there is a container which is having some liquid filled in it, and there is a solid spherical block which is attached by the bottom of the container by a help of a rope. So this rope is having some tension T0 initially when the container is at rest. So it clearly means that when A is 0, then obviously T0 will be acting in the downward direction, mg will be acting in the downward direction, and buoyancy will be acting in the upward direction. And as T0 is non-zero, so we can predict that buoyancy will be greater than mg, and T0 will be equal to buoyancy minus mg. Okay, so this is T0. Now buoyancy can be written as V into rho into g, and mg can be written as V into sigma into g. So T0 is equal to Vg, and this is rho minus sigma. This is the tension T0. Now when this container is accelerated in the upward direction, then we can say that the new buoyancy will be, V dash will be V into rho into g plus A, and the new tension T will be equal to the new buoyancy minus mg plus A, because pseudo force will also be acting on the ball in the downward direction. So T will be equal to new buoyancy will be V rho g plus A minus this is sigma V g plus A. And if I take common, T will be equal to V into g plus A is common, and it would be rho minus sigma. So T by T0 will be equal to V is cancelled and rho minus sigma is cancelled. So it would be g plus A upon g. So therefore we can say T will be equal to T0 into 1 plus A by g. So the correct option will be option A. Now we move on the next question. In this question, you can see that there are two solid spheres A and B of equal volume but of different densities. These are immersed in a liquid of density dF, and these are connected by a rope. Now this rope is in, this system is in equilibrium, and this rope is taunted. So we have to choose the correct option. So first of all, we know that on A, buoyancy, see, if A was alone and A was having the tendency to go in the upward direction, and if B was alone and B is having a tendency of going in the downward direction, then when we will connect them with a string, then a string will be taunted, which means that the tendency, natural tendency of A should be to go in the upward direction, and natural tendency of B should be to go in the downward direction. So we can say that dA would be less than density of fluid and dB would be greater than density of fluid. Okay, so this is the first thing. Now secondly, we can say that this system has buoyancy BA plus BB acting in the upward direction and MA plus MB G acting in the downward direction, and tension is an internal force, so we are not considering the tension in the free body diagram of the complete system. So we can say that buoyancy A plus buoyancy B will be equal to MA plus MB into G. Okay, and buoyancy A will be V into DFG, and buoyancy B will be V into DFG, and MA will be V into DAG plus MB will be V into DBG. So cancelling VG, 2DF will be equal to DA plus DB. So the correct option will be A, it would be D, B, and it would be D. Now we move on the next question. In this question, you can see that there is a container which contains two immiscible liquids of density ρ1 and ρ2. Obviously, the lighter liquid is ρ1 and the denser liquid is ρ2. And there is a sphere whose partial volume, half volume, is in this upper liquid and the half volume is in lower liquid, and this sphere is floating in equilibrium on the interface of these two liquids. The height of liquid column of liquid 1 is h, and we have to find out the force exerted by this liquid on the upper hemisphere. So let us first of all draw the diagram of upper hemisphere, and first of all let us draw this like that. So we are rubbing this part because we are concerned only with the upper part, and obviously the liquid above this will be applying a force F1, let's suppose F1 in the downward direction on the curved surface of the upper hemisphere, and let's suppose that the liquid at this point is applying some force F2 on this hemisphere. I know that you are thinking that liquid is not present inside this, so why we are applying this force? Because we are just imagining this hemisphere, that if this hemisphere was alone, then the difference of F2 minus F1 would be the buoyancy. We are just imagining this situation. So F1 would be equal to F2 minus buoyancy, and F2 will be the pressure at these points into area of the base. Now at these points pressure would be P0 plus H rho G, and the base area is pi r square, so F2 will be this into pi r square, and buoyancy will be the volume of sphere inside the upper liquid. It is 2 by 3 pi r cube into rho 1 into G. So F1 will be equal to P0 into pi r square plus pi r square H rho G minus buoyancy, which is 2 by 3 pi r cube rho 1 G. So P0 pi r square plus this is H minus 2 by 3 r, and this is pi r square rho 1 G. So the correct option will be option number A. Now we move on the next question. In this question, you can see that there are two identical containers which are having same volume of water filled in it, and they both are separately placed on two different weighing machines which are presenting the same reading. Now there is a hollow ball which is immersed in this second container, and it is connected with a string with the bottom of the container, as well as there is a solid ball whose density is greater than that of water. It is connected with a string which is connected to the roof somewhere out of this system, and this ball will sink down to the bottom if this string is removed, and this ball will float up to the top if this string is removed. So we have to, the volume of the two balls is same, so we have to find out that which of the weighing machine will present the greater reading or smaller reading, or whether they will provide the same reading or not. So let us analyze the first situation. In the first situation, as we can see that the tension acting on the ball will be balancing mg minus buoyancy. Let's suppose the mass of the ball in the first case is m1. So T will be equal to m1g minus buoyancy, due to the fact that m1g will be greater than buoyancy because the density of the first ball is greater than that of liquid. And this complete system will be having mg. Let us suppose that the mass of liquid in both the containers is capital M. So this complete system will be acted upon the external force mg, as well as the mg of the ball. This is m1g, and buoyancy is the internal force because liquid would be applying the buoyancy on the ball in the upward direction, and ball will be giving back its reaction in the downward direction to the liquid. So we are not considering the buoyancy in the free body diagram, but as you can see that this tension will be the external force, because rope is not the part of this system, because rope is hinged to the point which is not the part of this system. So if we consider the reading R1, then it would be equal to mg plus m1g minus T, and R1 is therefore mg plus m1g minus m1g plus buoyancy. So R1 will be equal to mg plus buoyancy. Okay, so this is the reading of the weighing machine in this case. Now in the second case, this string is preventing this ball from going up. So if we draw the free body diagram, then this buoyancy, the buoyancy will be same because volume of the two balls is same. So this buoyancy, and there would be a m2g acting in the downward direction, and the tension would be acting in the downward direction. But again, if we draw the free body diagram of the complete system, then tension will be the internal force, buoyancy will be the internal force, and the external force will be mg plus mg, m2g. So the reading R2 in this case will be mg plus m2g. Okay, and obviously we can easily predict that this m2g will be less than buoyancy, because this ball has a tendency of going up, therefore buoyancy will be greater than m2g. So this R2 will be obviously less than mg plus buoyancy, because m2g is less than buoyancy. So we can say that R2 will be less than R1. Okay, so the reading of the container, reading of the weighing machine in the first one will be greater. Now when we will cut this string, then this ball will move up to the surface of the liquid, and then also the system is experiencing this external force, and hence the reading of the weighing machine will remain same, and hence still then also we can say that R1 would be greater than R2. So nothing will change if we will cut this string. Now we'll move on the next question.